Uber serves 150 million reads per second, not requests, rows at peak. The same workload served straight from the database would need around 60,000 CPU cores. With a cache in front of it, Uber serves it with 3,000. 20 times less compute. 99.9% of reads never touch the database. Now, here's the part most explainers skip. The pattern Uber uses to do this isn't the simplest one, it's the one that puts the most work on the application. It's called cache aside, and there's a reason production picks it over the alternatives that look easier on a diagram. 3 patterns. They look almost identical on a whiteboard, but one of them owns a problem the other 2 pretend doesn't exist. By the end of this video, you'll know exactly which races break which pattern and why write-through doesn't always mean what you think it means. Ache aside. The application is the orchestrator. The cache is a passive store sitting next to it. Happy path first. The application asks the cache for a key. The cache has it. The application gets the value back. 2 arrows. Done. Now the miss path. Same first arrow. Application asks the cache for the key. Cache says miss, so the application falls through to the database itself, directly. The database returns the row. And here's the step that's easy to forget. The application also writes the value back into the cache. That's the populate step. Without it, the next read misses again. Notice what just happened. The application talked to the cache, got told no, talked to the database, then talked back to the cache. 6 arrows, 3 components, and the application is touching every edge. That's cache aside. Writes split into 2 flavors. Both put the application in charge. They differ in what they do to the cache afterward. Variant 1, invalidate on write. The application updates the database acknowledges, then the application deletes the cache key. Whatever was there is gone. The next read of that key will miss, fall through to the database, and repopulate fresh. Lazy? Simple. And what? We'll see in a minute. The most exposed to thundering herd on the next read. Variant 2, update on write, same first 2 steps. Application updates the database, gets the ACK, but instead of deleting the cache key, it sets the cache key to the new value directly. Looks safer, right? The cache is fresh immediately. It isn't. This shape is more vulnerable to read, modify, write races. 2 writers can interleave their database commit and their cache set, and the cache ends up with the loser's value while the database holds the winners. Write through. Cache is still the orchestrator on the read side, and now it owns the write side too. Application sends the write to the cache. The cache is the target. The cache synchronously writes through to the database. Database acks the cache. Cache acks the application. The write is durable in both places before the user's request returns. Notice the responsibility split. The application sent 1 write to the cache. The cache fanned out to durable storage. The cache is the write target. That's what canonical write-through means. The same definition Martin Fowler's responsibility model would give it, the same one Redis's documentation gives it. Now, here's where it gets messy. If you read AWS's caching docs, you'll find a flow labeled write-through that looks like this. Application writes to the database. Database acts. Then the application sets the cache. The cache is never the write target. It's reactive. That's not write-through. That's cache aside with an update on write branch. The same shape we drew 30 seconds ago. The name write-through implies the write goes through the cache. If the cache isn't the write target, the name doesn't fit. Same diagram in 2 vendor docs, 2 contradictory definitions. When you read a caching post and see write-through, check what the cache is doing in the diagram. 3 application servers, 1 popular cache key, the key just expired. All 3 servers ask the cache for the key at the same moment, 3 misses in parallel. All 3 application servers fall through to the database at the same moment for the same row. 1 expired key just turned 3 application servers into a denial of service attack on the database. This is thundering herd, and it gets worse the more popular the key is. 1,000 servers, 10,000 servers all hitting the database for the same row in the same millisecond. Failure mode 2. 2 actors, a writer and a reader. The writer updates the database commits. As far as the database is concerned, the new value is now the truth. But the cache wasn't told. The cache still holds the old value. The reader, meanwhile, asks the cache for the same key. The cache returns, perfectly happily, the stale value. The cache and the database disagreed at one specific moment in time. The reader caught that moment. This isn't a topology bug, it's a timing race, and it can't be fixed by choosing a better pattern. Every cache that's eventually consistent with its source of truth has this window. Failure mode 3. A cache node failed and restarted, or a fresh node just spun up. Either way, the cache is empty. Every read misses. Not because the keys expired, because nothing is populated. And the database carries the entire load until the cache rewarms. Salesforce wrote about this in early 2026. They were migrating their marketing cloud caching from memcached to Redis at 1.5 million requests per second. One scene closer at the production fix. Uber Cache Front Flux, August 2025. The application writes to the database acts the application. The user's write is done. The application has already returned. What happens next happens in the background. The database emits a change event, the same write captured from its replication log, into a CDC service. Uber calls theirs Flux. CDC asynchronously deletes the cache key. Notice what we just did. The user didn't wait for the cache to be invalidated. The write returned the moment the database committed. The invalidation happened on its own schedule, driven by the database's own changelog in a different process on a different timeline. 3 patterns, 3 columns. Cache aside. Application owns the mishandler, the populate, and the invalidation. Bites you with thundering herd on miss and read modify write races on update on write. Read through. Cache layer owns mishandling. Application is simpler, but you've moved the orchestration into the cache layer, you haven't deleted it. Same races, different place to fix them. Write through. Cache owns the write fanout. And important. Only if your vendor's diagram actually has the cache as the write target. If it doesn't, you're looking at cache aside in a misleading hat. Production picks cache aside not because it's the cleanest diagram. It picks it because when something goes wrong on a write, the application is the only thing in the system that has enough context to fix it. And read through and write through both move that context into a layer the application can't reach. Uber serves 150 million reads a second by keeping that control where the consistency problem actually lives. The patterns are stable. The operational practice, the CDC pipelines, the leases, the timestamped invalidations, is what's changing. And those changes happen on top of the responsibility split, not instead of it.